Hey, good morning, folks. Today we're going to start on Chapter 7, and you'll find with Chapter 7 that it's really just a repeat of Chapter 2, and then Chapter 8 is repeating again Chapters 3, 4, 5, and 6. So we're sort of recapping everything that we've done, except now instead of looking at things that are occurring in a straight line or, in 2D space, we're looking at things as they rotate around a fixed point. So even if you didn't do so well in those, I think that it will have helped that you've seen that material before, and the material that we'll present, it'll be sort of more condensed for rotational motion, and so we won't go in as great a depth as we did in chapters 3 and 4, for example. But we'll see all the same stuff, like with acceleration and velocity, and it'll be worked out largely the same. And then we'll also see momentum and energy, but all in terms of rotation. Okay? How's that sound to you? Exciting? Yeah? Now we shall have 5, 6, and 7. But 7's a pretty short chapter. We might get just a little bit of chapter 8 in there, but we'll decide that when we get back from the break. But for now, just look at 5, 6, and 7. I'll only add chapter 8 if it benefits you. So I'll add stuff from chapter 8 that's just really straightforward, and I'll tell you exactly what I'll be looking for, and it's still a lot of material on the test. Y'all have big plans for the weekend? Or the long weekend, because I don't know if you knew this. Did y'all know this? It's fall break. Fall break number 2. Did you know that? Yeah. We are... Yeah, I'm standing up here, I'm talking, and nobody seems to notice. And yeah, still nobody seems to notice. All right. But anyway, it is fall break, so we'll return back here on Wednesday, and Tuesday lab, we don't have lab on Tuesday either. Okay? So as I said, we're talking about rotation. We'll particularly talk about the rotation of rigid bodies. In Chapter 9, we'll start talking about the rotation of non-rigid bodies. That would be fluids, fluid rotation. We'll sort of dip into that just a little bit. But for now, we'll just talk about rigid bodies. And in a rigid body, we define a rigid body in that all parts move at the same angular velocity. And also, the parts do not move with respect to one another. One another. So, for example, I could be a rigid body if I just don't allow my arms to shake around too much, and if I move like this, then every part of my body is moving with the same angular speed. So if I'm moving at, say, 1 revolution per second, then that means the tips of my fingers are moving at 1 revolution per second. My elbow is also going around at 1 revolution per second. And every other part of the body is also moving at 1 revolution per second. It also means that, the distance between parts does not change. And you get that anytime you have a solid that's rotating. So we'll be talking about solid rotating bodies. So, for example, I can have a disk that is rotating around a particular point. As I said, if it's moving at 1 revolution per second, then every point on that body is also moving at 1 revolution per second. And then also the parts of the body don't move with respect to one another. They're fixed in space. They're not going to, the distance between 2 points isn't going to change with time. Non-rigid body, I mentioned this, but a non-rigid body would include something that is a fluid. Fluid is anything that flows. We'll get into that in Chapter 9. Non-rigid body, let's say water or a gas, can rotate, but it does not have the same angular velocity necessarily. And then also points can move with respect to one another. The axis of rotation, we'll define that for all of our bodies as they rotate, and it is the axis about which a body rotates. And the same body can have different axes of rotation. This will become particularly important in chapter 8 when we start talking about moments of inertia. The same body can have different axes of rotation. So for example, a person can rotate about all sorts of axes, especially if you're very coordinated like I am. You can rotate about this axis, right? Just spin around like that. You can rotate about other axes too, like you can rotate about this axis. You can do a forward, what's that called? A forward flip, a front flip. You can do other things. I can rotate about this axis. You ready? That would be a cartwheel. And so you can rotate about all different sorts of axes. And some axes are easy to rotate about, like this one. This one is very easy to rotate about. But other axes, like this one, are very difficult to rotate about. Or this one, which is harder, this one or this one? This one's harder? Okay. Yeah, so, you have to be fairly athletic in order to do those things, as well as, I don't know, not really hold dearly onto your life too much. Okay, we're going to go through and define all the stuff like we did in Chapter 2. Where, remember in Chapter 2 we defined displacement, velocity, and acceleration. We're going to go through and define those things, and you'll see that the equations are, well, they're exactly the same. So the way that we deal with them will be a little bit different, but largely it's going to be the same. And as I said, the problems won't go as quite to the same depth as we did in Chapters 2 and 3. The first is angular position. Angular position is theta. It measures a distance on the circle, so it's given in degrees or radians. So the SI unit for theta is the radian. Other units, of course, include degrees and revolutions. We would begin theta naught, our theta initial, is almost always equal to 0 degrees or 0 radians. Remember your unit circle, just to remind you, because we'll be seeing your unit circle quite a bit here. I have 0 degrees here. This is 90 degrees, 180 degrees, 270 degrees, and then back to 360. And then also know it in radians that I go from 0 to, pi over 2, pi, 3 pi over 2, and then back to 2 pi. So remembering your unit circle will help you in this chapter, because we'll be talking about a lot in this coordinate system. Does anybody remember what kind of coordinate system this was? We mentioned it in Chapter 1, but we haven't seen it since then, where we give a point in space as r and theta. Recall? We have the Cartesian coordinate system. This is called a polar coordinate system. You probably use that in Calc, I don't know, Calc 3 maybe. Well, y'all don't take Calc 3, do you? No. Well, if you took Calc 3, you'd use the polar coordinate system to do various intervals. Okay. I'm sorry, go back. You need to know how to convert between these different things. So remember that 2 pi radians is equal to 360 degrees is equal to 1 revolution. The SI unit for angles is always going to be in radians, and so if you ever have any doubt at all, just convert everything to radians. By the way, it doesn't matter in this section if your calculator is in radian or degree mode. Actually, no, it does matter. It needs to be in degree mode, because whenever we're dealing with angles where they're related to our trigonometric functions, you'll need to be in degree mode. So even though our angle for theta is in radians, you'll need to be in degree mode, not for Chapter 7, but for Chapter 8. I'll try to remind you on your test, but just make sure that you get your calculator in what, degree or radian mode? Degree mode, even though we're using radians here. It's really only relevant when you use your trigonometric functions. All right, angular displacement is the difference in our angular position. So delta theta will be theta final minus theta initial. So for example, let's say that I go from here, we'll call this pi over 4 radians to, what will be the next one? Pi over, no, not pi over 2. What's between pi over 3? Thank you. So this would be theta final. This would be theta initial. Notice that these are just measuring angles. If I want to know then the net angular displacement, that is the angular displacement between this point and this point, then it would be pi over 3 minus pi over 4. So delta theta, for example, here would be pi over 3 minus pi over 4. All right? You need to know also the sign convention, and this is just a convention. I don't know if there's a reason. There might be a mathematical reason that we do this. But whenever we have counterclockwise displacement, like we did here, this is counterclockwise, we're going to say that that's positive. Whenever we have clockwise displacement, we're going to say that's negative. And so, for example, this helps me to remember it, is to always remember that clocks, they go in the wrong direction. And I told my lab about this, but you guys, I don't know if y'all get these catalogs with like all these dorky science things in them. Do y'all get those like t-shirts with F equals MA on the front? Do y'all get those catalogs? No, I guess they just send them to me because, I don't know, you buy t-shirts with F equals MA on the front. But in those catalogs, you can also buy a clock that doesn't go in the wrong direction. See, because this clock is going in the negative direction. You can buy clocks that go backwards. And you too can have one. The lower cost is like $25. Okay? Okay, so just know this, that counterclockwise is positive, clockwise is negative. Whenever you're dealing with motion, that'll be sort of like our direction. It's not really the same as we had before, but you need to know that counterclockwise is positive and clockwise is negative. Okay, so our angular displacement was theta. Our angular velocity we're going to call omega. This is the Greek letter omega. It looks like a W, but it's a little more rounded. It's the lowercase Greek letter omega. Okay? So we'll call angular velocity omega, and our angular velocity is going to be defined as, well, we'll have a couple of things. We'll have our average angular velocity. Now, just to remind you, I'll sort of write this off to the side. Back in Chapter 2, we defined average velocity, and it was delta x over delta t. That was our average velocity, which was, x final minus x initial over our change in time. We're going to have something very similar here. It'll be delta theta over delta t. That is theta final minus theta initial divided by your elapsed time. I'll just keep it as delta t. So we have that as our angular velocity. This is our average angular velocity. And our instantaneous angular velocity. Remember how these are different. This one is the average over a period of time. So if I have theta versus t, and it looks something like this, the average velocity is between 2 points. So it would be like the slope of that line. That would be the average velocity. On the other hand, our instantaneous velocity would be the velocity at a particular point. Make sure you know the distinction between those. This is from Chapter 2, but it's still relevant here. Average velocity averages over a particular time. It's only dependent upon the initial and final positions, not on anything in between. The instantaneous velocity is the velocity at a particular point. It's the derivative of that function at that time. We can define this as the limit as delta t approaches 0 not theta, but 0, of delta theta over delta t. But of course, that's just the definition of a what? Calc 1, folks? It is a limit, but it's more particular. It's a derivative, right? So this is d theta dt. That's our instantaneous velocity. Now, you're not actually going to use this. I just want to show you that the instantaneous velocity is the average velocity, but just so that I collapse this time interval down to a particular point. That's what a derivative does. It collapses the denominator down to a particular point, an instant. All right, if the angular velocity is clockwise, the sign is what? It's negative. If it's counterclockwise, it's positive. Same convention for velocity as what we had for displacement. Okay, now let's look at angular acceleration. We have a couple different things here, just like we had before. For angular acceleration, we're going to call this the Greek letter. Do y'all know what that is? It's alpha. It's our Greek letter alpha, lowercase alpha. So remember, we have theta is our displacement, omega is our velocity, and now alpha is our acceleration. I don't know any good way to memorize that except just, put it on a note card and paste it to your cabinet door or something. That's what I do. So that'll be the hard part, is sort of connecting our linear quantities to our angular quantities, just remembering these new variables that we have. So we can call our average acceleration is delta omega over delta t. Same idea as what we had before with angular velocity. If I have a plot of omega versus time, and it looks like this, the average acceleration is between 2 points. This is equal to omega final minus omega initial divided by our time. And then in a similar way as we did before, we have our instantaneous acceleration, which is the limit as delta t approaches 0 of delta omega over delta t. So it is, you let this time interval get really, really small. That's your derivative, and that gives you your acceleration at a particular instant. It's d omega dt, and I could plot it, say, right here. That would be our instantaneous. I'm sorry, not omega, but alpha. And similarly here, alpha. Exactly the same argument. We're just looking at rates of change in our position and then rates of change of our velocity when we're looking at acceleration. So nothing new here, really. We're just giving them new variable names. We're going to have some new units attached to them. We're going to use radians instead of meters. But exactly what we saw in Chapter 2. Just new variable. There's one little change. Clockwise is negative. Counterclockwise is positive, just like we had before. We're going to begin to see the right-hand rule just a little bit here. This isn't terribly important right now, but it becomes more important in the next chapter, and then it becomes even more important in next semester when we start doing magnetic fields, is the right-hand rule. I'm just going to sort of introduce it here. Well, even though it's right here, you're not going to, never mind. Let me take that back. So we can find the direction of these angular vectors. Imagine, if I have something that's moving in this direction, have a disk, say a merry-go-round, you're looking down on the top of it, and it's rotating in the, the counterclockwise direction. So we would call this, a positive velocity that has a positive velocity, but that doesn't necessarily give its direction. In fact, how would I draw the direction of this? If I think about it up here, I might draw the direction in that direction, because the top of the thing is moving in that direction. But down here, I might draw it in the downward direction. So I can't really capture the direction of this vector in any way with the counterclockwise. There's actually going to be a different way that we think about the direction of the vector, and that is using the right-hand rule. And I'm not going to get too much into this, but we will see it again next semester. We're going to give the direction of these vectors where we let our fingers wrap in the direction of the rotation, and then our thumb will give the direction of the vector. That doesn't have much physical meaning for you right now, and don't sweat it if it does. It doesn't really matter. But we're going to let our fingers go in the direction of the rotation, and then our thumb will give the direction of the vector. So the fingers wrap in the direction of the rotation, and the thumb gives the direction of the vector. So for example, with this disc, which is rotating in the counterclockwise direction, what is the direction of the velocity vector? Is it into the page or out of the page? This is out of the page. So omega here is out of the page. We call that the plus z direction, and we would use this symbol to represent it. Out of the page, I'll just write plus z over here. We use a symbol like an arrow that's coming straight at you. If I have, if you're looking at the page and there's an arrow coming straight at you, it would look like this, the point of the arrow. Have you ever had an arrow come straight at your face? No, that's a good thing. But if you did, that might be what it would look like, because you would just see the point of the arrow. On the other hand, if I have an arrow going away from me, what's it going to look like? You're going to see the fletching, and the fletching will look like this. So if I have something in the negative z direction, it's going to look like this. This is into the page. So if I have another disk that is rotating in the opposite direction, omega is into the page. I let my fingers here now follow the rotation, and now my thumb points into the page. Always use your right hand for this. This will come up on the concept test in just a bit when we see it again. But it's not going to be a big part of this exam, but it will be next semester. You'll see it a lot more. Okay? May I go down from here? Okay, so you have the equations on the equation sheet. If you're not familiar with it yet, you really need to be familiar with it. Here's the various equations that we'll have for Chapter 7, but I'm going to give them to you here. But first, just let me remind you of the equations that we had last time. We had V is equal to V naught plus AT. And then also, we had x is equal to x naught plus v naught t plus 1/2 at squared. And usually with this one, we said, well, x naught is 0, so we're just going to leave this thing off completely. And our initial position is almost always 0. As far as we're concerned, it is. It doesn't have to be, but it is. So now we're going to make some substitutions. In fact, we could do the same derivation. We went through this derivation in Chapter 2, but I'm not going to do it here. Where we can say, well, now my x will become theta. And now my v will become omega. And now my a will become alpha. And all those same equations will apply. So I'll have, instead of v equals v naught plus at, I'll have omega equals omega naught plus alpha times t. And I'll have theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And just like we did before, we'll say, well, theta naught, we'll just call that 0. We'll just set it equal to 0 whenever we have a problem. So I have the same two equations that I had before. Just notice the variables have switched around. X has become theta, v has become omega, and A has become alpha. In a very similar way, as we move through chapter 8, every variable that we've seen for, momentum and energy will stay the same, but work and all force, all those variables will find that they have counterparts in the rotational system, but the equations are all going to be the same. You can look at your equation sheet and you'll probably actually recognize some of them. Okay? How's this sit with you? Okay? All right, let's, we will sometimes want to translate our linear equations. Oh, I'm sorry, no, this is just saying that x is theta. We'll just skip down. Oh, shoot. Hold on, don't move. Let me just look at something. Disconnect to my notes here. Okay, so sometimes we'll want to be able to translate angular quantities into linear quantities. And we're going to do that, well, if you think about your unit circle, right? I have an angle theta, I have a radius r, and when I move from this theta I to theta f, I transcribe a certain distance. So I have a certain arc that I travel through. We can find that arc, or that linear distance. This is the arc. It is a linear distance. And it is equal to theta times r. You follow what I'm doing here? This is just the arc of a circle. If I go from this distance, from here to here, angle theta, the distance that I travel along this is equal to that angle times the radius. What happens if I let that angle go to a full 360 degrees? What does the arc of the circle become? It becomes the circle, right? Because that's the circumference. The circumference is 2 pi, which is my full 360 degrees times r. So sometimes we'll need to figure out the linear distance, and we'll do this here by multiplying theta in radians times r. So remember, let's make a little note here, radians, 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 always. If you ever have a doubt, you're not going to have to translate all of your units. Like sometimes we'll encounter problems where you won't need to convert units necessarily, but you'll never go wrong converting your units to radians. Okay? We'll do some problems. I'll show you what I mean. Now, in a similar way, I can convert my speed v is going to equal to omega times r, and then also my angular acceleration, my acceleration a is going to equal to alpha times r. You can think about the units here because omega is in radians per second, and r is in meters. And if I combine those, we just sort of drop the radians, we get meters per second. The radians isn't really a true unit anyway. But if I multiply meters times this 1 over seconds, then I get meters per second. Or if I multiply radians per second squared times meters, then I get meters per second squared. So this allows me to convert my angular measurements into linear measurements. That's exciting, isn't it? Like, y'all look excited about it. Okay, let's do a practice problem. Watch your units here. In general practice, you always want to look at your answers and see what units they're put in, and then look at the data that you have and see what it's offered in. you're sort of split between B and D here, so about half and half. Think about, talk to one another about what you think the right answer is. It is either B or D. All right, let's stop in about 10 seconds. Stop at 2:40. Does anybody know what my dad did as a living? I've told y'all before. What did he do? Yeah, well, he worked at a tire shop, but yeah, he's a mechanic of sorts. He wasn't really a mechanic, but he sort of was. But so as a kid, like I just have fond memories because my brothers, we all started working there. We just swept floors and stuff at like 12 or whatever, 11, and we would crawl through the tires because they put the tires in those big long racks, you know, and it was like a tunnel. You could crawl through them. All right. Okay, good. B is right. I think it's right. Let's work through it. So the first thing you want to do here is convert your 3.2 revolutions to radians. I say 1 revolution is 2 pi radians. And so that's going to be 6.4 pi. What is that? 19-ish? What is it? 20? 20 even? We'll just call it 20. All right, so 20 radians. And then I want to know its angular acceleration. Well, I know t is 2 seconds. I also know that omega naught is equal to 0. And so I say theta equals omega naught t plus 1/2 alpha t squared. So I get 20. This is 0 equals to 1/2 of alpha times t, which is 2 squared. And so alpha is 20 divided by 2, which is 10. So B is the right answer. That is in radians per second squared. So notice, and you'll find this on these questions, that sometimes our angles are given in revolutions or degrees, because that's just sort of more common to give measurements in revolutions or degrees. But whenever you're using these in the equations, they must be in radians. Well, that's not entirely true. We'll see some other examples where it's not true. You could do it all in revolutions, but your answer would be in revolutions at the end. But just to be safe, you can always convert it to radians. Let's see, let's do a couple more. We'll go to the back and see what kind of trouble we can rustle up. All right, let's do page number 21. This is exam, should be about exam 3 or maybe 2. Yeah, exam 3. Let's do number 21. Between midnight and 3 a.m., the hour hand of a clock has what displacement? Have an awesome joke if y'all get this one right. All right, we'll stop at 120, 120, just 10 more seconds. Okay, good. This is right, because between midnight and 3 a.m., midnight is up here, 3 a.m. is over here. I go through 90 degrees, which is 90 degrees is pi over 2 radians. And so it's either A or C. And so now the question is, if I'm going in this direction, is that positive or negative? And by our convention, that is a negative displacement. Let's see. Let's try number 20 over here on the previous page. 2,600 revolutions per minute is equivalent to which of the following? Number 20 here, it's on the previous page. Feel free to ask your neighbor. Y'all doing really well. We'll stop in about 15 seconds. You'll see some conversion problems likely on the test. Stopping at 115. 115. Awesome. C is right. 2,600 revolutions per minute. I say 1 minute is 60 seconds, and 1 revolution is, what am I going to, radians, is 2 pi radians. If you're going to degrees, you put 360 there, and that's equal to, what was it, 270? And that's equal to 270. All right, that's in radians per second. All right, so C. Hey, how did the farmer get his wife? He tracked her down. Camille told me that one. Okay. Let's see, maybe there's another one here we can do. Yeah, let's try number 26. 26. And click in on your answer. Number 26. All right, we're going to stop at 101 minute, or 105, 105. All right, folks, we had problems like this before where we want to know how does theta change with time. Theta is omega naught t plus 1/2 alpha t squared. Omega naught is 0 because it's at rest. So I'll just get rid of this whole term right here. And I'm left with theta equals 1/2 alpha t squared. If I travel through theta in time t, I want to know what happens if I change t to half its original value. If I take half of t, because it's squared, I have to have theta over 4. So D is the right answer here because of that quadratic term. You'll see questions like that. We've had questions like that, but they'll just be now with different variables. Instead of x, we'll have theta. Instead of v, we'll have omega. Instead of a, we'll have alpha. So with a little practice, you should be able to do that, hopefully with some ease, but you'll certainly see some like that. Let's do a few more clicker questions. Don't forget family day this weekend, y'all, and football game at 3, I think, right? 3? Time at 3? I understand they're pretty good. Okay. Huh? So Bonnie and Clyde are these two bunnies on this merry-go-round. It's going around in a circle. Clyde sits midway. Bonnie sits at the edge. How do their angular velocities compare? We'll stop in about at 130. Stopping at 130. Okay, very good. That's a rigid body, right? A rigid body, all the points on a rigid body have the same angular velocity. But that's how we define what a rigid body is. Let's see. Did you hear, some of you have heard this actually, I'm sorry, but did you hear about the stormtrooper who had a Wookiee steak? It was a little chewy. Okay, Bonnie sits on the outer rim. Clyde sits midway. Again, same thing. Makes one revolution every 2 seconds. Who has the larger linear, or sometimes we'll call that tangential velocity? Who has the larger velocity as we would measure it in, say, meters per second? All right, we'll stop at 55. 55. Okay, good. B is right. Bonnie has the larger tangential velocity. Remember, our V is equal to omega times R. They both have the same omega. So if R is bigger, like it is for Bonnie, then her speed is going to be bigger. You feel like you're going faster on the edge of a merry-go-round than, say, in the middle of a merry-go-round. Suppose that the speedometer of a truck is set to read the linear speed of the truck, but it uses a device that measures the angular speed of the tires. That's what a speedometer does, actually. And then it converts that into a linear speed. You follow what I'm saying? It measures omega, and then it converts it into V, which reports on your speedometer. What if you took the small tires off and put on larger diameter tires? How would that affect the speedometer? Would the speedometer read a higher speed than the true linear speed, a lower speed than the true linear speed, or will it still read the same true linear speed? You put bigger tires on your truck. All right, about 5 more seconds. At 1:05, I'll stop. 1:05. Okay, good. It is going to read a lower speed. So this is the true speed. V is equal to omega R. Omega is going to stay the same for your vehicle, but if you increase R, that increases V. So if you put bigger tires on your truck, then for the same revolutions per second, your truck will actually go at a faster speed. But your speedometer still thinks you got those little bitty tires on your truck, and so it reports a lower speed than what you actually are traveling. Okay? Yeah, with me on that? I always have to think through it. If I put bigger tires on, the truck actually goes faster, given the same angular speed of the hubs or whatever. But your speedometer reports a lower speed than what you're actually traveling. Yes? Sort of? All right. An object at rest begins to rotate. Oh, yeah, so, well, we've already done this one. I'll let you. Let's read it. It's the same as the previous question we had. All right, let's stop at 35. Okay, good. B is right. But no joke for that one because we've already done that question. But remember, theta is 1/2 alpha t squared. If I take half of t, it's squared, so I get theta over 4. Expect to see some questions like that dealing with theta, omega, and alpha. This one's similar, but a little bit different. All right, I'll stop at, hold on, come on, we can do better than this. Listen, omega is related to t in a particular way. How is it related to t? How is omega, alpha, and t all related to one another? And then if I take half of my t, what's going to happen to omega? That little w, the little curly w thing? What's going to happen to omega? All right, I'll stop at 122. All right, A is right. Omega is equal to alpha times t. If my t goes down by a factor of 2, that means that my omega is also going to go down by a factor of 2. Or let's just do, let's do this one. You have to remember back what we talked about with acceleration and velocity and their sort of relative directions. Remember, if I'm slowing down, my velocity and acceleration are opposite directions. If I'm speeding up, my velocity and acceleration are the same directions. You'll recall from chapter 2? Slowing down, they're opposite directions. If I'm speeding up, they are same direction. All right, let's stop at 1 minute. 1 minute. 5 more seconds. Just guess if you're not sure. Okay, I think that's right. So first of all, is traveling in the clockwise or counterclockwise direction? Clockwise. So that means that omega has to be negative because it's clockwise. And then it says that it's slowing down. So that means that alpha will be opposite the direction of omega. All right, so clockwise means omega is negative. Because it's slowing down, alpha is opposite omega. We'll do this one. This will be our last one. 5 revolutions per second is what in radians per second? And while you're doing that, I'll tell you this. It's not really a joke, it's more of a story, but I'm expecting that you'll do well. So my family and I, we were out sort of traveling around down the bayou, just exploring and stuff, and we saw this sign on the side of the road that said zoo. And so we said, hey, we're going to go check this out. And so we went up to this zoo, and we got there, and the only animal that they had was a dog. They just had one dog in the entire zoo. Do you know what it was? It was a Shih Tzu. I'm sorry, that's a little vulgar, I know, I'm sorry. But it's just a dog, right? All right, y'all have a great weekend. Have a good fall break. D was right here, D.